Welcome everybody, welcome to our Wheel of Fortune. Let's spin it and see where it lands. We got a secondary, how do we know that? Well, primary, secondary, tertiary is really simple. Put your finger on your halide, drop it to the carbon, check out the number of hydrogens. You only have one, which means it's secondary. Chiral, well, we don't have a planar symmetry in this direction or in this direction, so therefore it's chiral. And then the next thing is it RRS. So if you look at this, you're going to go 1, 2, 3, hydrogen out. That's going to be an S. So let's start with this and try to see what it's going to do with good nucleophiles. Is it going to do the same thing as it did with primary, or is it going to do something different? The good nucleophiles, being good nucleophiles, cannot be basic and do an E2, rip off hydrogens or ionize. Therefore, if you have a good nucleophile, you either have an SN2 or an SN2. There's no alternative for most of these. Now, if you have a secondary, it's basically going to be backside attack. If you have tertiary, now that's a different story, okay, with these nucleophiles. But with primary and secondary, it's going to be SN2. We are doing a secondary and it's chiral. Now there is a chiral center here and there's a chiral center here. So this molecule can have enantiomers and diastereomers. So let's see what we're going to get. The chirality here is going to be 1, 2, 3 with the hydrogen going away from you. That is going to be also an S. All right, let's look at what this can do. Let's take the big PPH3. Okay, well, it's going to come in here. There's a lot of steric, so it's going to be slow. But there's nothing else for it to do. It's either attack or just lie low. So it's going to do what it can do. And depending on the conditions, it could do SN2 and give you a inversion. So your nucleophile is going to attack from the backside, opposite. So it's going to attack from the opposite side of the chlorine, kick your chlorine in the back and get rid of it. So your nucleophile is now going to be on top because that's where it's going to come in. So here is your PPH3. It lost its lone pair. It's positively charged forever. NaSH, same deal. Sulfur, big, polarizable nucleophile, powerful nucleophile, comes in, attacks from the top, kicks it out, and gives you a nice chiral inversion. Now you cannot change the chirality at this center because that's fixed. That's a hydrocarbon, but you will invert the chirality at the carbon chlorine or carbon halogen bond with an SN2. So all SN2s would be an inversion. And well, all of these again are going to give you the same result as before. Selenium, really nice big negative nucleophile, pushes out your chlorine by attacking from the top. So this is going to go bam on the top. Now you may wonder, since this is a 6-membered ring, does it have to be axial like in the case of a E2 where you had to have diaxial? Let's draw it out. So we can, let's say you have your chair here, and in this case you have a chlorine and a methyl. The chlorine is going down, let's say, and your methyl is also going up. So your this is not a favored conformation. This is trans, and so this is trans. This is going to go mostly to this. So your starting material will not be able to have the chlorine in the axial position. Your chlorine would be in the equatorial position. So when you flip this up, chlorine's down, it's going to be down. Methyl's up, and it's going to be up. And this di-equatorial is going to be way, way more stable than this diaxial. So this is the stable form. So this is where you're going to react from. Can you react with an equatorial halide? In the case of a, let's say a SN2, let's say you're bringing in a cyanide here, you don't really have to get into the beta carbon and align orbitals. The orbitals are aligned like this. So this carbon minus is going to go right in the back side here and kick that out. So being equatorial is fine because you have a nice exposed backside there with just a hydrogen, and you can do an SN2 like that. So here you're going to get a product where you would have your incoming nucleophile now being axial. And that could flip over depending on the size. This is a small nucleophile, so it's better for this to be axial than this methyl because it's got all these hydrogens that can bump into the hydrogens in the ring and do 1,3-diaxial. So this might be the more favored conformation. So basically, you're quite fine having an equatorial leaving group because your chlorine and your nucleophile can be in a straight line. And that's really the most important thing for an SN2 because those p orbitals, that p orbital that's here has to be shared by the chlorine and the carbon at the same time. And that's only possible if you have a straight line. So therefore, SN2 can happen on axial or equatorial. Even if it's on the axial, you can have a straight line here for the cyanide. However, this is unstable or high energy, and so this is going to go to the low energy form and react from there where your chlorine's equatorial. Now, this is going to be different when you get to E2 because in E2, you got to have a diaxial. All right, I just want to make sure that you understand the difference between E2 and SN2 when you come to chairs. All right, let's talk about the next one, sodium thiocyanate. So that is going to be pretty much doing a backside attack, coming on top, attacking and kicking that chloride out. So let's draw these in the chair like we've seen before. Let's say you have your parallel lines, dot, connect the dots, and your methyl here is on your carbon 2, and your incoming group is going to push that out, and you are going to get a thiocyanate, SCN. Exact same thing here. And I've been drawing them out, so look at my previous videos for the resonance structure. And you have your iodide here. In this case, iodide is really big, so it may want to flip to the other chair where you have the iodide being equatorial. So it depends on who's bigger. The big honcho guy gets to decide, you know, which chair form is favored. So this is going to be probably more here than here. Same with your NaNO2. NaNO2 is, well, kind of a medium nucleophile, but it's still good enough to do an SN2. It's probably going to be really slow, and you are going to get a nice nitrate. NaOAC, well, now you're getting into kind of a basic zone. This is secondary. There's a lot of steric here. Can you do a backside? Or is it going to favor an E2? Let's look at that. Sterics don't really affect E2 as much because in E2, you're pulling out hydrogens on the neighboring carbons, not on that. So here's a weak base, and is it going to do an E2 or an SN2? According to the literature, there's more SN2 than E2. So over here, you can see minor E2. Now that's probably substrate dependent too. So I'm going to draw both of them. In this case, it's going to be major, minor, but you may have to take it case by case. Here's a neutral amine and NHMe2. That's also going to do major SN2 because, as we said before, nitrogen is also a very good nucleophile in addition to being a base. So that is going to give you NMe2 after you deprotonate the hydrogen with another NHMe2. So this is going to be methyl groups here, these sticks. Minor is going to be E2. This is going to be your major. SN2, minor E2. Let's move on over here. Well, this is also part of the nucleophiles, but when you have a secondary, they are going to be basic. So this is a good base and a good nucleophile. And if you have a secondary, this does more E2 than SN2. If you have a primary and a primary that's unhindered, it's going to do SN2. Let's look at it. This is going to pull off a hydrogen and do an E2. Same here, hydroxide, methoxide, ethoxide, propoxide, all of these are going to pull off a hydrogen next door. Which one? Because we have choices here. All right, so here are your B-class bases. They're small, they're powerful, and they want a proton. And that's all they're really interested in. Now, they have choices. They can either attack here or pull off these protons. Because they're so basic, they are going to go for the hydrogens, and they're not really interested in SN2 as much because there is some steric. So therefore, they're going to pull off a hydrogen on this beta or this beta. Let's call this beta 1 and beta 2. Where do you think it's going to pull off? Small bases. Small bases are governed by Zaitsev rule. And Zaitsev, we know, has said that if you have more friends holding hands on that pi bond when it's forming, you're going to go much faster over that hill. So that's what's going to happen. Who's got more friends? Well, if you pull off this hydrogen, you're going to have a carbon here, and a carbon here donating. 3 friends. If you pull off this or this hydrogen, and we'll see which one, you are only going to have 2 friends. Well, 3 friends any day is better than 2. I don't know if that's always the case when it comes to roommates, but you know, in this case, that's how it is. So let's draw out a chair form and see which one's going to be pulled out. Now, in the chair form, where do you want to put the chlorine? Do you want to put it axial or equatorial? That's right, this is a chair, and we said in chairs, actually, in all E2s, you need to have diaxial leaving groups. That means the hydrogen and the chlorine should be on opposite sides and flat 180 degrees apart. Let's draw out a chair for this so that chlorine would be axial. So here is a chlorine, and that's going to be going down. And that would then make it only be available to eliminate with a hydrogen that's going to be diaxial. So over here on this carbon 6, you have 2 hydrogens. No sweat, that's fine. But over here, look at this. The methyl is the one that's going to be sticking up, and the hydrogen is going to be down. So here, your methyl is going to go up. So even though it really likes to go with this hydrogen and have more friends, the methyl is kind of coming up that project because it's axial, and so you can now eliminate a whole carbon. So you have to eliminate this hydrogen with the chlorine and form the Hoffman product. Okay, so this is kind of a little different. It's a twist. So for all of this, I'm going to put OR or OH. This is going to then run them to the electropositive carbon here. So the electronegative chlorine can run away with the octet. So once you've taken off your hydrogen and had a pi bond form here and the chlorine out, you're going to get a very nice alkene. That's going to be a Hoffman alkene. And if I draw it flat, it's going to be a little easy to see that. And so that's going to be major and major for all of these. That's your major product. And that's going to be major E2. Do we have minor products? Sure we do, because you do have a secondary center. These are small bases. You would have some minor. Let's draw the minor SN2 products for the 4 of them here. And the amount of minor would depend on many things, on the nucleophilicity of the reagent, the size of the reagent, the amount of steric, and so on. So it's almost impossible to predict a percentage, but all we know is even if you have a little teeny bit of minor, it's going to show inversion at the chiral center. So if it's an inversion, your S would be an R. So the first one, let's say this is a ethoxide, you would have an OET. If this is a methoxide, let's say over here, this is your minor, and you will have an OME. If you have an hydroxide, you will have an alcohol. So these are both ethers, and you will have an OH here. And if you have an acetylide, you're going to have very, very, very minor SN2. Well, I'll just throw that in. You have to look at the literature for this particular molecule, but it will be mostly E2. All right, so here's your B class. B class basic nucleophiles would be E2 more than SN2. A class, mainly good nucleophiles, would be SN2. Let's look at your very, very basic and sometimes very bulky bases, C class. Are they going to do any SN2? Not really. With T-butoxide, it's almost zero. I would say zero SN2. DBU, DBN, they don't do SN2. Sodium hydride, really not a good reagent for SN2. For all of them, you would put just E2. And the way the reagent is, obviously it wants to pull off the less substituted hydrogen. So it's not going to go for this. Even if your methyl here is equatorial and your hydrogen had been axial, it's still going to go for these just because of the steric there. So for all of them, you're going to get this exact same Hoffman elimination. So this is Hoffman elimination, and so that's going to be the case whether you have a small base or a big base. All right, let's move on to our D class. Really, I mean, these are kind of at the lowest rung of our reagents. They're just solvents, and sometimes they're mostly side products, kind of a unintended consequence. So let's look at what would happen if you had a nice fresh bottle and some kid came in, opened the bottle, left it on the countertop and went home. It's going to absorb moisture, and that moisture is going to really unravel that molecule. So that's one of the things that you don't want to do, is open up a nice bottle of chemical, leave it on your bench top and go home. You're going to come back to somebody else. Secondary. So let's see what happens. Let's draw a mechanism for this. This would be the same for all three of these. Your chloride comes off and you would get a positive charge. So your chloride here would ionize in these protic solvents, and that's going to give you a positive charge. So the hydrogen's remaining, it's flat. Now this is going to be secondary because we know there's a hydrogen here. So then you can have two things happen. You can have a hydrogen move over, and so then if you have a positive here, well, it's going to look to its neighbors for help. If the hydrogen can only come over with its sleeping bag and all, and have a sleepover here, you're going to get a tertiary. So obviously sleepover is the best solution here. So you're going to have your neighbor come over. Now it's going to be fun, fun, fun. You're going to have a tertiary. Tertiary carbocation in a protic solvent is going to get attacked directly, and you are going to have, let's say, methanol or water, some protic solvent. Let's say in this case I'm using water. It's going to bind to that. SN1 is going to happen faster than E1, and so you will get, after deprotonation, a nice alcohol. And it's going to be the most substituted alcohol. A minor product would be E1, major SN1. And then if you take off a hydrogen, again, when you have E1, you're always going to do ZF because you're going from an intermediate. You're not going from some transition state like this. Because you have an intermediate, now you have a pause to think which is the best one to pull off. If you pull off this or this, you'll have a tri-substituted alkene. But if you pull off this hydrogen, it's only going to be di. So obviously, tri over di. That's your minor E1. And that would be the same over here as well. So with methanol, something really similar happens. You're going to get minor E1. You can see instead of a hydrogen, you're going to have a methyl. And so the reactivity would be almost identical mechanism. And your major is going to be your ether, OCH3. So what about acids like HBr, HI, H2SO4, and so on? Well, HBr and HI, if it's concentrated, the bromide or the iodide, depending on what the acid, is going to act as a nucleophile and give you SN1. Because these would be gases, so you typically come in water, and so there would be water, and so water would attack, and that would also give you a side product of an alcohol. What's the mechanism? Well, because it's so protic and ionic, it's going to rattle that and give you a carbocation, which is then going to have a rearrangement, and it's going to give you the tertiary carbocation. That's going to be attacked by the bromide. And then just like before, you would also have some elimination E1. So here you will have bromide plus the water. And in this case, they're all achiral. If you had another chiral center here, you would draw up and down a raceme. But in this case, they're achiral. And so you have an OH as well. And that would be your major. And depending on the concentration, you'll get a different mix of products. And then the minor is going to be your E1, just like you saw before. So major and minor. Great. Well, what does ammonia do with a secondary? Turns out ammonia is a good nucleophile, and it does more SN2 than E2 for most of the reactions. So SN2 more than E2. So there, and then just like in the primary, we saw ammonia is going to attack this, and then the hydrogens on the ammonia are going to get deprotonated and make it more nucleophilic, and it's going to keep attacking more and more of this until you're going to have all four of them substituted by this same molecule. So that's going to give you four of these on the nitrogen. That puts a positive on the nitrogen, and your counter ion is going to be your chloride. So you get an ionic product there, and that would be kind of soluble in ammonia, and then you can do whatever you want with that. A lot of the fabric softeners and stuff have tetra-alkyl ammonium chlorides. There are lots of products out there in the market, and this is also used for making soft soaps and laundry detergents and a whole slew of products. So therefore, this is a very useful reaction in industry. One of the things about the A group nucleophiles is the reaction on a secondary, especially a secondary with a beta branch, would depend a lot on the solvent and the pKa of the conjugate acid of the anion. For example, these aren't very acidic, but HCN has a pK of around 9. So if you had HCN in an aqueous, then you would have different things happen. So that would be SN1. So I'm going to put note HCN in aqueous would be SN1. And if it's SN1 and it's next to a branched carbon, then you can get rearrangements. So continuing along these lines, you could say that if you had aqueous, then you would have dissociation of the chloride, and then you would have the hydride migrating, 1,2 hydride shift. That's going to give us a carbocation here. That's tertiary. Now the tertiary carbocation can be attacked by the cyanide up and down. In this case, it really doesn't matter just because it's achiral. So you would get a typical SN1 type of reaction here on the tertiary carbon, where you would put the cyanide on the more substituted carbon. Another example is NaNO2. Let's say this is going to be in DMF. However, if NaNO2 is in aqueous, the pKa is about 3.1, which is quite acidic, which means it can ionize this and pretty much do the same thing as here. So I'm just going to put a note here. NaNO2 aqueous can do SN1, which means you're going to have the exact same thing happening, where you're going to have dissociation of the chloride as it's shown, and you will have the hydrogen then move over 1,2 hydride shift to give you a tertiary carbocation. the tertiary carbocation can then be attacked by the NO2. And also if it is aqueous, then you'll also have water. So in all of these cases, when you have aqueous, a side product would be alcohol. So this plus your water attacking that, and it would depend on the concentration. What is the concentration of the cyanide? If it's really high, then you get mostly this. If it's dilute, then you're going to get a lot of this. Again, same thing. This can be attacked by NO2 minus, and it really doesn't matter which direction, just because you are going to have a chiral molecule here. And if you attack with the water, then you'd have to deprotonate. So that's why I have two arrows here. And that would be the same for acidic. You're going to get NO2 up and down. In this case, it wouldn't really matter. And since there's aqueous water here, you would get attacked by water, which then gets deprotonated to hydroxide and gives you a nice alcohol. So these are some of the things that, we should bear in mind. It's the same here. If it's in an acetic acid media, then you're most probably going to do a SN1. All right, so I hope you're comparing the primaries and the secondaries and seeing the major differences. The main difference really is in the small base nucleophile region. Primary would give more SN2 here, secondary would give more E2 here, and branched primary would also give more E2 here. But whereas A class, the nucleophiles are concerned, primary and secondary would give you SN2. What's the difference? Primary would be a lot faster than secondary. And if you had aprotic solvents, it would make it even faster. Now that doesn't mean it's not going to go in protic. It would. Sometimes protic could ionize it and give you a raceme. So we would like to do aprotic, especially when a chiral center is involved. So we don't have any ionization. And we want to have a specific stereoisomer. All right, so let's see what your fortune holds. And when we come back next time, we're going to do a tertiary. Well, let's spin it. Talk to you soon, guys. Bye.